Okay, so the HL Chem review, we're going to start covering bonding. Okay, two terms to know: intramolecular, which is within the molecule, so this would be covalent bonding. And then we have intermolecular, and that is between molecules. Okay, this would cover like your melting and freezing. Okay, and then your boiling or evaporation and your condensing. Okay, so for these intermoleculars, you are breaking just intermolecular forces, not covalent bonds. Switch back to my yellow color. Alright, so since I start off defining two terms that have to do with molecules and molecular bonding, it makes sense that we're going to take a moment and talk about ionic bonding. I was kidding, it doesn't really, but that's where I wanted to go. So ionic bonding is the transfer of electrons, okay, and these form ions that are then electrostatically attracted to each other. By the way, all of bonding is actually all about electrostatic attractions. Wanted to look at a couple of diagrams. I'm going to pause this while I draw them, and then we'll be right back. Okay, we have returned. If we look at, this is the sodium ion here. I'm sorry, sodium atom. Here's the chloride atom here. If you notice, the chlorine atom is supposed to be about half the size. Try to write it nicer. I don't like that color either here. Let's go with this color. This is about half the size of the sodium atom, right? The idea is in the ionic bonding, the sodium gives up its electron here. All right, and if you notice, I tried to draw the sodium bigger. It's probably not quite twice as big as the chlorine atom, but I tried. The X's represent the electrons. They are drawn in pairs, representing the 2 electrons per orbital. You see the rings around the nucleus. Those are the energy levels. Okay, once sodium gives up its electron, the remaining electrons have a greater attraction for that positive charge in the nucleus, and it goes down about half in size. The chlorine atom gaining that electron gets larger, roughly about 2 times larger, because of the added repulsive forces, right? This whole process, hopefully, you can relate to the Born-Haber process that was talked about earlier. Okay, so that kind of tries to go give you reviews a bunch of stuff at one time. Okay, moving on. Formulas for ionic compounds. Okay. Remember, ionic compounds are formed roughly or generally between metals and nonmetals. And all ionic compounds are neutral. Okay, so that's all ionic compounds. All right. Periodic table. Hopefully Okay, not counting hydrogen. Okay, and I do actually want to do just this a little bit. Everything in this first group is a +1. Hydrogen is 2 sometimes. Everything in the second group is a +2. Aluminum is a +3. Zinc is a +2. And silver is a +1. And you can see it goes down on that diagonal. Halogens -1. Group 6 is -2. And nitrogen, phosphorus, -3. Okay, those are the ions, stable ions that they form. For cations, really named just using the element named. Okay, for example, Na+ is just called the sodium ion. For anion, you're going to change the ending to "ide." Some of them, like for example, Cl- is the chloride ion. Some of them are a little weird. P-3 is the phosphide ion. S-2 sulfide ion. You should say ion. Remember that F is fluoride. Please don't write the L in the symbol. N-3, and I should do it the other way, is the nitride ion. All right. And then when you name them, you just put them together. Sodium chloride, sodium phosphide, sulfide ion. You make sure that they are neutral. So sodium chloride would have 1 sodium, 1 chloride. Sodium phosphide needs 3 sodiums for every 1 phosphide. Polyatomic ions. These are some you just have to memorize. The charge is distributed across the entire ion. That's why we use the brackets when you're drawing the Lewis symbols. This is the nitrate ion, carbonate ion, hydroxide ion, phosphate ion, sulfate ion, hydrogen carbonate. All right, things like for iron 2 hydroxide, remember, put the parentheses around the polyatomic. Okay, transition metals. Remember, these can have more than one stable oxidation state. So for an iron 2, we would call this, I gave it away, iron 2. You might also have an iron 3, where you need to use Roman numerals to signify the charge on the ion. Aluminum, zinc, and silver only have one stable state. Remember, included in these that need Roman numerals needed for tin, lead, antimony, and there's one more. It's in that group of 4. I don't have a periodic table open. Give me a minute. I'm going to pause you. I'll come back. Bismuth. All right. Well, we're just about 10 minutes, and we're done. I'm done talking about ionic compounds. So